Hello and welcome to Partially Redacted, a podcast where we discuss privacy and security engineering and related topics. I'm your host, Sean Faulkner, and today I'm joined by Avradip Mandal, Senior Software Engineer at Skyflow, and we'll be talking about homomorphic encryption. Avradip, welcome to the show.
Hi, Sean. It's my pleasure to be here today.
Awesome. Yeah, thanks for joining. I feel like it's been some time since we've talked, so why not on a podcast? We're going to take a deep dive into a popular but maybe not super well understood topic, homomorphic encryption. But before we get there, can you share a bit about your background, work history, how you ended up where you are today?
Yeah, sure. So I did my PhD in cryptography and I was really fortunate to start my PhD at the time when fully homomorphic encryption was the hot research topic. And some of my work set the early milestone in the current generation of homomorphic encryption research. And after my PhD, I worked as an engineer in Microsoft for some time. Then I moved to research and joined Fujitsu Lab as a researcher. Over there, I worked on variety of topics, but primarily focusing on cryptography, security, blockchain, and quantum computing. And then I have been with Skyflow for about a year. So I work in the privacy preserving encryption team. It's really exciting for me to see all the things that we invented as academic researchers, and they're actually getting used in our product and making a difference.
Yeah, it's amazing. I think whenever, I was a former academic too. And I think one of the reasons I left academia was I felt like the lead time from essentially some contribution I made in academics to actually being realized in a real application was too long. And I wanted to get out there and actually build stuff that would impact people today. But yeah, it's amazing. And you starting essentially your research in fully homomorphic encryption, and now actually seeing some of this technology like realized in the real world is probably really satisfying for you.
Yeah.
So what kind of you mentioned your research at Fujitsu? What exactly were you doing there?
So in Fujitsu, uh, I've been working in many areas. So as in blockchain and homomorphic encryption, as well as security. So we essentially our idea was we are inventing new cryptographic scheme and security schemes, and so that people can use it. And down the line, some of our engineers were actually implementing those.
Oh, okay, so this was essentially the research arm of Fujitsu,
Yes,
and
exactly.
they were looking at like forward, future types of technologies and stuff like that.
Yeah.
So, moving towards the topic at hand, homomorphic encryption, I've often heard this described as the holy grail of encryption. So why is that? And I guess what is exactly homomorphic encryption and how does it kind of work?
Yeah. So homomorphic encryption is any encryption scheme which allows homomorphic operations over ciphertext. So what it really means is it allows us to perform encrypted operations on the ciphertext without knowing the secret key. So if you give the secret your ciphertext to the server doesn't have the ability to decrypt it. Still, it can do operations, and it can give you back the encrypted result, and then you can decrypt the result and find what you wanted to know.
In operation, do you mean essentially that I could take, let's say, two encrypted numbers and add them together to get some sort of new value?
Yeah. So when they're basic operations, it's like that. So you can do additions and multiplications, but that's how the regular homomorphic encryption is. But when you talk about fully homomorphic encryption, what we mean that it should allow us to do any arbitrary operation. That means, suppose uh, given a file, we should be able to know whether the file match has your face on it or not. So these kind
Okay.
of things, like anything, you should be able to do.
Yeah. So essentially, any operation that we can perform on data today without encryption, we should be able to perform while under this encryption scheme.
Yes, exactly, and that's the promise of the promise of the Holy Grail, the fully homomorphic encryption.
Yeah. Okay. So that's like the promised land. So where did
Yeah.
this concept come from, and what's sort of the history with it?
Yes, it actually has a very long history. So, like the basic encryption scheme that we perform, which is like RSA, which was invented in 1977, right? And this is actually multiplicative homomorphic. That means you can do any number of multiplications on the ciphertext, and then you can do the decryption once you have the ciphertext. Uh, and that time people thought, okay, we can do any number of multiplications, and why not? We can also do any number of additions, right? And once you can do multiplications, additions, that actually any number of time, that's actually fully homomorphic. Just with those two operations, you can do basically anything. And that's the point the people thought about that problem in late 1970s. But then this problem was open for a long time. People simply couldn't do it. There are many homomorphic encryption schemes which are partial, in the sense you can do either some unlimited number of additions or unlimited number of multiplications, and there is also one scheme in which you can do unlimited number of additions and one multiplications, but they were nowhere near what we can call fully homomorphic encryption. And that was actually invented in 2010. And when Craig Gentry had kind of a real breakthrough, he used something called ideal lattices. And using that, he was able to build a partially homomorphic encryption scheme, which means it can support some limited number of additions and multiplications. And not only that, then he showed how you can kind of bootstrap that scheme. That means using that scheme, you can actually build a fully homomorphic encryption scheme that can allow you unlimited number of multiplications and additions. So that's when the theory was when it was theoretically known that we can do fully homomorphic encryptions. And after that, now there has been 10 years of research. And from there, the things are much more practical compared to that time.
Has anybody, so people have implemented, I'm assuming, partial homomorphic encryption schemes, but has anybody been able to implement a fully homomorphic encryption scheme, even if it's not essentially performant?
Yeah, so I think right now we have the libraries that you can use that to build fully homomorphic encryption schemes, but it will be really, really slow if you just want to do arbitrary operations.
So why is it so slow?
So the main reason it is slow is how the fully homomorphic encryption works. So when you think about operations or regular operations, say we want to do some search, right? And so over there, when you do the search, we are thinking about like a Turing machine model, right? You can run some loops. So it's like a generic programming language, right? But when it comes to homomorphic encryption, we need to convert that whole operation to a circuit, which means you don't have a Turing machine where you can do a loop, you can do some breaks, those kind of things. Everything needs to be circuit in the sense that you can do everything in terms of additions and multiplications. And that causes a huge blow up in the size of the circuit depending on what you can do. Especially you can think of like the edge cases where sometime in a circuit, in a computation, you are stopping and sometimes you are not, right? For example, your regular operation can be, usually it takes say 1 second, but there might be some edge cases that takes 1 hour, even though that doesn't really happen often, right? But when you make it a circuit, it is always going to take 1 hour.
Mm-hmm.
And that's one of the huge impact.
Did I understand this correctly, that essentially the process for supporting fully homomorphic encryption is that the operation that you want to perform ends up getting translated into a like sequence of additions and subtractions, and that essentially, like, that's a limited set of things that you can do, so that is going to blow up essentially, that depending on the complexity of the operation, the number of steps that you need to execute, and that's why it's slow.
Yeah, so that's one of the reasons. So that's the first reason is you're making it circuit, and the second reason is even after making it a circuit, the individual operations are really slow because now those operations are happening in an encrypted space where before it was just a operation over 1 bit, and now it is an operation over like megabytes of data.
Mm-hmm. So how does something like that compare to other forms of encryption that we're used to using, like various like popular symmetric or asymmetric encryption schemes?
I mean, these are kind of different notions, right? So when we talk about asymmetric and symmetric encryption schemes, Over there, they don't really care about performing operations over the encrypted ciphertext, right? Or over the ciphertext. Over there, our only goal is to make the encryption and make sure nobody can break the encryption. And from the encrypted data, if you have the secret key, we can decrypt. And when we talk about symmetric encryption scheme, we assume there is only one key, and that key is used for both the encryption and decryption. And for asymmetric encryption scheme, you have one public key that you can use for encryption, and the secret key is only for decryption. And
Mhm.
the same things can also happen in homomorphic encryption. So homomorphic encryption can also be either symmetric or asymmetric. In fact, the first scheme, the somewhat homomorphic encryption scheme that Craig Gint proposed, it was actually symmetric. And then he showed how you can make it asymmetric. So there you can think of they're happening in a separate kind of dimension. So homomorphic encryption scheme can also be symmetric or asymmetric.
I see. Yeah. And then are there any sort of real world applications of homomorphic encryption today?
Uh, Yeah, so it all depends on what you want to do in the end with the homomorphic encryption. So I think today the things are fast enough, so you can do some relatively simple stuff. For example, you want to do linear regression over the ciphertext, or maybe you can even run some very simple neural network inference, such as say you want to detect some digits. Those things are, I think, possible today.
Mhm.
But the main challenge is kind of figuring out what's the correct use case. And even in the correct use case, you are always going to have some performance penalty. And you need to decide whether the security is worth that performance penalty or not.
Right. Yeah. I mean, even with other encryption schemes, you're going to add some sort of performance hit versus if you don't use encryption at all, because you're adding some sort of level of operations that are going to have take up CPU cycles, right?
Yeah, but I think those are, I think, regular encryption schemes when you don't care about homomorphic encryption, like operation of ciphertext. I think now today those are fast enough that you
Right.
don't really see it. They're almost hidden behind, say, the network latency.
Mhm.
But when it will come to homomorphic encryption, you are going to observe the real, like some delay. And the question is it okay or not?
Hey there, it's Sean, host of Partially Redacted. You probably guessed that, since at this point in the interview, you probably recognize my voice. I've been told for years that I have a face for podcasting, but no one has mentioned whether I have a voice for podcasting, so sorry about that. Hopefully, the awesome guest makes up for it. Anyway, if you're enjoying this episode, please support the show by subscribing and telling your friends. You can also join Partially Redacted community at skyflow.com/community. Okay, that's enough for me. Back to the show.
In terms of the latest developments in this area, are there some recent breakthroughs to in with respect to homomorphic encryption, like research or actual implementation?
Yeah, so there has been like some steady but very good progress over the last 10 years. So we can say that if the Craig Gentry's the first invention was like say the first generation, probably we are now in the fourth generation of homomorphic encryption schemes. So now I think if you just do a quick Google search, probably you see more than 15 or 20 homomorphic encryption libraries. They all kind of serve, they either use different schemes or they kind of serve relatively different purposes. But I think the one that I'm most excited about is there is the library called HEAN, like HEAN. So this is kind of changes the ball game how people can use homomorphic encryption. So earlier, I think the before this, the goal of homomorphic encryption or when you build a library, the goal was to build always to find out the exact result, right? So if you are adding some ciphertext, the final goal is if when you decrypt, you want to have the exact result. But
Mhm.
this library kind of changes that. So here they don't want to really guarantee that final output would be exact because in many cases that's not what you want, right? For example, if we want to decrypt an image, we don't care if the image decryption is exact as long as the final result looks good enough, it matches the original one, we're happy. So some small noise is actually okay in many cases. And this library actually uses that fact. So they perform approximate homomorphic, you can call it approximate homomorphic encryption. But that advantage is then it becomes many times faster if you could have done the exact one.
So how does that compare, like so I get this many times faster, but do you have an example of essentially like, if you were to do this operation, let's say the image example, do that using one of the other encryption schemes that is looking for like the perfect match? How long would that take in terms of like seconds or minutes versus this, other approach that uses approximate?
Yeah, so I don't have the exact number, but my kind of educated guess is probably it will be like about 100 times faster than doing the exact one.
Okay, so pretty significant.
Yeah.
And then what are some of the like challenges or obstacles that need to be overcome in this area? Essentially, in order to get to a point where we can have fully homomorphic encryption at a level of performance that's similar to other forms of encryption that we're used to using today.
To be frank, I don't think that's going to happen in anytime soon. That we'll always be hitting some amount of the performance penalty. But as with everything, maybe there will be a time when that penalty doesn't really matter. So maybe our homomorphic encryption is still, say, 100 times or 1,000 times slower than regular encryption. But still, it might be okay because for the applications we are interested in, that amount of delay doesn't really matter.
So it could be more about like deploying it for specific types of use cases where the delay or whatever the delay is less impactful than something like you're currently loading a web page or something like that.
Yeah. So maybe if you're loading a web page, you already have a network latency, right? So maybe it will be at the same order, so it doesn't really matter. And also, it also comes about the security. Like homomorphic encryption, you want to use it in the case when you really care about security. And maybe that there are scenarios where that performance penalty is okay.
Right. And then, are there limitations of using fully homomorphic encryption, not just, outside of the performance issues? Or is this essentially like the gold standard that everybody's kind of moving towards, at least when you're talking about, having the greatest security around the type of data that you're storing? So once we've achieved this, can we essentially just be like, great, we made it. We can all go take a nap. We don't need to continue research in this area.
I don't think that's ever going to be the case. I think the main reason is homomorphic encryption doesn't promise you everything that you want. It's very specific to what it can do. And in many scenarios, you don't really need homomorphic encryption, right? For example, homomorphic encryption is applicable where the client or the actual user, they can manage their own key, right? So because the basic promise is server cannot do anything. So server is not allowed to have the secret, and client wants to hold the secret by themselves. But in many scenario, I think that's not the case, right? The regular people are not that interested in actually holding their secret key. They want to offload that to some trusted server. So in those scenarios, maybe it might be the case. We don't really need the homomorphic encryption. So it always depends on what is your security goal and for the specific scenario, what you want to achieve.
What do you see as the impact of homomorphic encryption on, say, the future of data privacy and security?
Yeah, so I personally think actually it might be a good thing that homomorphic encryption cannot do all operations and things are slow, right? Because there are scenarios. So right now, what happens once our data is stored in the server? For any operation, we need to give the server the secret key, and the server potentially can do anything on that on our data. But with homomorphic encryption, what might happen that it will allow the server only to perform a limited set of operations. And that might be a good thing in terms of security and privacy because we don't want that to happen.
Mhm.
So, but I think realistically, we are still kind of far away from kind of deciding on what can or cannot be done by the homomorphic encryption scheme. But
Yeah.
that's, we can think of open research and probably will solve something. So.
Right, and even if you had performant fully homomorphic encryption, it doesn't necessarily solve all of your data privacy challenges. Like you still need encryption key management. If you have to deal with things like right to be forgotten, deletion requests, you still need to be able to have a way to track down where all that data is. Um, you know, just because it's encrypted doesn't mean the data isn't in 1,000 different locations, for example.
Yeah, exactly. Yeah. In the end, homomorphic encryption is just another tool in your toolbox. In the end,
Mhm.
depends on how people can use that.
Yeah. And then, what advice would you give to organizations or individuals that are considering, investigating into using homomorphic encryption?
I think the main thing is to understand what are what the homomorphic encryption promises and what are the limitations at present or what will be the limitations in foreseeable future. And once you can have that understanding, you can figure out the scenarios where it is actually useful and you should use it, and there are scenarios where you cannot use it.
In terms of the research and breakthroughs that are going on in this area, are they primarily being driven by the industry, or is it still primarily from like academic institutions, or maybe a combination?
Yeah, so I think now it's a good mixture of both. So there are academic institutions, academic researchers who are heavily involved, and as well as some um, homomorphic encryption libraries are actually coming from industry. For example, Microsoft uh, it has the homomorphic encryption library called SEAL, which is one of the leading libraries, and I think other players such as IBM and is also involved.
Mhm. And then besides homomorphic encryption, are there other future looking privacy and security technologies that you're interested in or particularly excited about?
Yeah. So beside homomorphic encryption, right now there are other forms of encryption which are called functional encryptions, and those are really interesting in for the cloud applications because what homomorphic encryption guarantees you that only the key owner can know the final the encrypted data, can know the plain text or decrypt the data. However, the server cannot, it guarantees it cannot really know anything. But in many cases, we don't really want that to happen, right? For example, say I want to search my picture uh, from my photo storage. And
Mhm.
if it is homomorphic encryption, there is no way for the server to know which photo is actually matched with my query. So it will just dump me the whole storage. But if it is a functional encryption, maybe it won't know what the photo is, but it can still detect the match and it can give me the correct photo. So I think that direction of research is really interesting and might be actually more impactful than homomorphic encryption.
Yeah. And then what do you think about the work that's going on sort of in confidential computing and like secure enclaves where there it's not necessarily about having like an encryption scheme that can perform all these different types of operations over the fully encrypted data, but essentially instead creating like a walled garden environment that's hardware based that where the operations happen within the secure environment. But that's the only place that they can happen is within this, essentially the secure enclave.
Yes, I think they are really promising in terms of what you can do right away today. So without waiting for homomorphic encryption or or functional encryption to be practical. So they are of course not as secure as compared to the encryption scheme where the guarantee comes from some mathematical hardness. So
Mhm.
here the guarantee comes from the security of the hardware, but it's still a guarantee that say the hardware manufacturer is standing for. And what it allows you to actually kind of flesh out your design in a secure way so that you can kind of make sure if something breaks, all the things will break inside the hardware container. So you can always separate your thread vectors.
Mm-hmm. Yeah. Yeah, it's really, I mean, we probably need to do a show on that topic at some point, but it's an interesting area that I think seems to be like gaining a lot of momentum, or there's a lot of excitement about it. For the libraries that you mentioned that exist for that implement these different fully homomorphic encryption schemes, are these libraries like open source or freely available for people to try out?
Yes, definitely. Yeah. So all these libraries that people are developing, they are all, I think, if not all, most of them are open source. So
Mm-hmm.
if anybody wants, they can try and play around with those libraries. But using the libraries can take some amount of ramp up time, because unlike regular encryption, homework encryption comes with many parameters, and you need to kind of tune those to get the actual level of security and performance. But once you get a kind of a hang of it, it's not so difficult.
Yeah, great. Maybe I'll try to track some of those down, or you can point me in the right direction. I'll include some of those in the show notes. All right, Avradip, thanks so much for coming on and sharing your knowledge and background regarding homomorphic encryption. I always enjoy talking to you. I learned so much. So feel free to come back anytime. Thanks and cheers.
Yeah, thanks. It was my pleasure talking with you today. It was really fun.